Uh, my name is Elvis. I'm presenting on what's called IoT on easy mode. This talk will help you guys who are interested in looking at embedded device hacking or reversing, and maybe help those out who have a little bit of experience but not so much on the exploitation side. So this is the outline. I'm not going to go through this. This is just like you can look at it once, take a picture, look at it later type thing. This is what we're going to go through. Basically, the idea is to walk through the software stack and the hardware stack. Basically, using the same processes and the ideas that I use in my own personal engagements to help me grow within this field. Since I've only been reversing embedded devices for about a year, maybe a year and a half now. So the generic who am I, right? So like I said before, my name is Elvis. I'm an IoT researcher by complete accident. So we'll talk more about that story as I go on, but random facts, I play games on Steam. If any guys want to hook up on Steam, play some Counter-Strike, cause some shenanigans, hit me up after the show. And I also enjoy participating in CTF challenges. I'm also known as Black Owl on Twitter. So the introduction, so what sparked all this? So before embedded devices, I was in the desktop space. I was looking at Internet Explorer, use after freeze, learning how to exploit those, just really looking at the desktop space. Until one day, a coworker of mine, ex-coworker, sorry, Headley Zeke came in and was like, hey man, I found this awesome vuln because I wrote this little fuzzer within 5 minutes just to find command injection within the UPnP interface that was dealing with SOAP messages. And I was like, great, cool, that's awesome. Until we looked at it a little bit further, and it was actually a big deal because it wasn't a problem with the manufacturer itself. It wasn't like TP-Link's problem or whatever the manufacturer was. It was an actual problem with the SDK manufacturer of that chipset. So any kind of vendor that used that chipset, that Realtek chipset, was using that UPnP service that they bundled with it. That's the vulnerability right now. So it was across many vendors. So it was kind of a big deal. So I thought to myself, well, if this is, he wrote some command injection fuzzer within 5 minutes to find this type of vulns, like there's got to be something great. Like I have all these devices at my house as well. So I go home, I'm all excited, and the first thing I do, I'm like, all right, hold on, let me take a step back. Like, what's the actual attack surface for this stuff, right? Like, I've never been to somebody's house, and they're like, hey, check out my router that's directly connected to the internet, everything's facing open, I have no firewall, like everything's completely open, my internal network is the WAN. I've never seen that. So I was like, all right, so I go into this little device, I look at the HP instance, it's using BOA, and I'm like, well, let's see what else is using BOA out there as well. So just like the awesome researcher that I am, and many of you do as well, I go on Shodan and I look for server BOA and not looking for version numbers or anything like that. I just want to see what the attack surface was. And there was over 1 million results that came back. I was like, oh, this is awesome. This is actually a legit attack surface. We can actually cause potential damage, right? I don't advocate that. But this is actually pretty cool. So let me dive in a little bit further and see what I can do. So within a few weeks, I found some pretty nasty vulns, anything from command injection to stack corruption. Basically, all these type of vulns are kind of like 1990 type vulns where we're sprint defing to concatenate a string for some reason, and then passing it to system, or we're just doing straight stir copies, not looking for length bounds, or using a byte within the message to pass a mem copy. So the things though with this type of stuff, I actually had to dig in a little bit because I used the same approach that my coworker Ricky used, and I wasn't finding squat. Everything, I fuzzed the HP service up and down, left and right, the headers, every single parameter, doing Konami codes, throwing everything I can at it, and nothing was working, and it got me frustrated. I'm like, he can go home and fuzz something in 2 minutes and get something awesome, and I'm fuzzing everything, I'm getting diddly squat. So what I had to do actually was start teaching myself about firmware extraction. So there's a great tool out there by a researcher known as DevTTYS0, Craig. He wrote a tool called binwalk, and binwalk basically will take a binary image that you have and look for the magic bytes through it to find different types of like structures are inside of there, or any kind of like executables, whatever it is, whatever's inside there, it'll extract it. It's an open source project, you can download it, it's great, it's really, really simple for any kind of binaries that are not like obfuscated or encrypted or anything like that. So just running binwalk-e for extraction and capital M for what's, I think, I may mispronounce this, but it's like Matrushka, which is like 8 layers deep. Just keep extracting. So it's a really handy tool. It takes about 5 seconds to install and extract binary images. So that's what I started at first. But the thing is though, this architecture that I was going for, the device that I had some vulns in, or wanted to find vulns in, sorry, I didn't know the assembly for it. Like I come from the x86, 64 background, And so I come from the pop ret times or the jump ESPs or using your ROP chain by the returns. So I'm like, all right, so I got to teach myself this assembly language for this processor, which is MIPS. It was a MIPS 1 instruction set in R3000 processor. So what I did to do that was I downloaded something called buildroot, and I made myself my own toolkit to cross-compile for my target architecture, and I can set the instruction set as well. So I know C pretty well, and I bet a lot of you out there know C as well. The last thing I want to do when I'm learning new processor is to read the assembly manual up and down and kind of just force it in. I'm a very visual person. So what I did was I'm like, all right, so I have a main function. I have two functions, test function and then main. So within main, like I see an initialization of 0 for this local variable. And so that I know that S8, also known as FP, is pointing to the ret val for this particular C application. So I know the 0 register is going into there, and then I call a function. I want to know how argument passing works. So in this one, we see A068, because hex 44 is 68 in decimal. So A0 is going to be argument value 1 or 0. And then the next argument that's going to this function as well is going to be 101 in decimal, 65 in hex. And then we have the return. So I see the same offset within S8, which was my ret value, right? So I know that V0, when coming back from a function, is going to be the return value from that other function. So now I'm starting to understand how the GNU compiler is starting to make this assembly code for my target architecture. And then again, I look at printf, and I see that ret value is going to be put into argument value 1, because the second parameter, first one's going to be my format string. And then finally at the end, we have these two instructions. So I don't know how many of you know MIPS, but MIPS is a 4-byte instruction set. So every single 4 bytes, it just processes that. So we have two instructions here in order to load this 43D word into the return, right? So what we can do is just, like we did with x86 when we were kind of not sure and stuff, we just set breakpoints. So the first thing I did was I set a breakpoint at LUI instruction. I can look it up, but it's nice to have the nice visual representation. So that's step 1. I make sure the instruction was executed, and now I see that the upper bounds of that register is now 4343 in V0, the return register. So then I step 1 again, and then now I see that the lower half, even though it's all null, it's going to be 434343. So now I know that if RRI is being executed and the lower n bytes, lower 2 bytes or so are null, that I know it's going to be popular with that value. So very, very quickly, I can start learning the basics of how this processor works, like how function calls works, how return values work, how initialization works. And it's very, very simple once you start digging into it a little bit further and further and trying to teach yourself this. But then we can also take a step back. Like, I'm a big fan of reading assembly, maybe a lot of you as well. But we can do this a little bit easier. So a lot of these devices I've seen, like home routers, not so much the embedded devices use RealTOS or RTOS, but a lot of these Linux systems fall under the GPL, the general public license. And so if that's true, then the source code might be out there. So if everything's under GPL, and if we take a quick look and just Google dork it up, for this vendor A, I just type in the vendor plus GPL source code, and there it is. I can look for my device. It has the complete toolchain to compile anything that I want for that device. So if I want to make new firmware, I can just download this and just mock it up and then upload it. I have a TV. My TV's on a GPL. Who knew? So we can keep going on and on. There's vendor C. We can just download this, like I said, and make our own. It just goes on and on and on. So we can take the source code instead. So instead of reading arbitrary assembly and trying to figure out what functions do, we can just download the source code and look at it directly and have a white box assessment instead of doing all this black box stuff. So that's kind of like the software side, very, very high level, pretty basic to get into. The hardware side is interesting. So this is like my IoT shopping list, you can say. So for the beginners, I would say I use this all the time. Like this is like my Swiss Army knife, my bread and butter. I use this all the time. Anything that's more, I don't really use that often. So the stuff that I use a lot, so this board up here, it's pretty small, I don't think you guys can see it, is also known as the FT232H. It's an FTDI chip that will do USB to serial. It supports JTAG, SPI, I2C, and UART. It is great. It's $15 off Adafruit. So if you blow it up, it's only, it's not that bad. So going forward, so the multimeter. So the multimeter that I have in my hand here was actually $30 as well. So it's brand new, all this stuff. The biggest things that you're going to be spending your money on the beginner list, it's going to be the multimeter and a soldering iron. If you have buddies that have this type of stuff laying around, just ask them to borrow it if they're not using it, so you can save yourself about 60 bucks. The biggest one is the FT232H. That's the thing that I use all the time. And the soldering iron to make header pins and all that stuff. But the main thing that we want with this, and I'll talk about it later, is about the continuity and having sound emissions for that. So as we go a little bit forward, you can have your intermediate, you can have your advanced lab, you can have the big super lab of your dreams where you have this awesome box where you're dropping nitric acid and you're decapping chips and doing all this cool stuff. But for the most 90% of it, you're not going to need any of that. So the beginner stuff is great. I would recommend you guys looking at that. If you need links or anything like that, I can provide those. Those are also at the end of my talk. So finding UART. So if we have a device and we want to see like what kind of pins are kind of available to us, but we don't want to open it up yet. Maybe it's under warranty and we don't really want to screw it up. What we can look for is the FCC ID. So any kind of wireless device has to go through this qualifications. And the FCC is very, very generous about providing very detailed photos about every device. So if I look at the FCC ID on their website, I see something called internal photos. And then right off the bat, boom, there's the main board, and I cropped it a bit. And those 5 soldered points right there, it looks like a serial interface. Like a lot of you will be like, that's UART, like done, drop mic. But that's right off the bat. I don't even have to open up the device, and I can see, all right, cool, maybe there's a UART device. It's right there. Let me solder to it, and then I'll go ahead and void warranty and cry about it later. So, the one thing that I want to give back to you guys and let you guys know where I screwed up a few times is the first thing you're going to do is find ground first. Like you're always going to find ground, because I've blown up a few of these things by being naive and plugging accidental power into ground and also power into input, and you get a nice smoke show afterwards. So to prevent that, this is the way that I found ground, was using that shielding that I ripped off, but part of it was still around. That was actually a common ground for the electronics. And this is the actual high level, this is how it works. So UART is basically it looks like, in a Linux environment, it looks like Telnet. It looks like SSH. It's very, very simple, very, very basic. It's just a command line you get at this point. And you also get a lot of output upon booting up, and you may be able to break out the bootloader, but that's a different story. But this is how it works, ground to ground, transmit to receive, receive to transmit. Very straightforward, right? But the problem is, if we're looking for UART, the one question is, what's the baud rate, right? I don't know about you guys, but I hate brute forcing myself around to figure out what is the baud rate for this serial interface. Is it 9600? No. 115200? No. It's kind of time consuming. So I have a logic analyzer that I got from Soleil. It's a Logic 8. I just hooked it up and I did a 20-second digital capture, which is very, very low, very small file. It was about 30K or so. If you do an analog capture, you get into the gigabytes and stuff like that. But for this, so I take this little image and I enhance it, and then I see that the lowest bit width, when the falling edge and the rising edge happen again, is 8.8 microseconds. So what can we do with that, right? So I don't need to find the most precision one. I don't need to find the exact one, which is the shortest. I need to find something that looks pretty short. So what we can do is take that bit width, which is 8.8. We take 1 second over the shortest bit length over for like a million. And then that's how we get our baud rate. Very, very simple for this type of interface. This is not going to work for everything, but for UART, this works beautifully. So I take that number 11363636, which is about 115200 for standards, right? So I plugged it into the analyzer that we have for the serial protocol that Soleil bundles. It's great. Plug in our baud rate, and it starts decoding the message. So it says right off the bat, this is the word start. And it ends with a space. Congratulations. So great. So now I know which port is the transmit on the device, and I also know which baud rate to use. The other thing that I do, it's kind of dirty. It's to kind of brute force your way around for the receive on the board. But that's just me. So going forward, so if you come across a UART interface that is password protected for any reason, you can't break out of the bootloader, you're just dropping to this username password thing, you can try to brute force it. There's been protections that if it fails about 3 or 4 times, it will wipe itself. I've never come across that, but I've heard of it. So the way that I've pulled images off devices is through the flash chip. So a lot of devices, like a bigger form factor, will have a dedicated flash device to hold all of its data, like the firmware and such like that. So I take this image and I look at the serial number that's printed on it, and this is the MX25L3206E. I just go straight to Google, type in that number. The second result is the data sheet. So I take the data sheet, and it will tell me the pin layout. So now I know exactly what pins do what, what's power, what's ground, what's the hold. Like all these, this is very, very important because within the data sheet, it will tell me how to put this into write protection mode so I don't accidentally screw something up. It's kind of like if we think about the 90s and we had floppies. You just put into write protection mode so you don't overwrite your stuff, right? Same thing, but with a little microchip. We can also look at the SPI interface that is looking, that the data sheet tells us about. When the clock is high, you will see this upon idle. If the clock is low upon idle, it will be in this mode. So I did a quick capture right before I came here, and we could see that when the clock is low, the chip select is high, and then we see the clock going, and then we see a little bit of the input kind of going up and down a little bit as well. So we know what mode this will be in, and as we go forward, we start shorting out the pins for hold and everything else. We'll start knowing how to extract the data out, because it will give you the instructions that it knows. Like this byte is to read an arbitrary length, and it will also give you the memory layout. So if you know the data sheet and you know the part number, everything else is pretty straightforward. And that little FT232H will talk to the SPI protocol for this chip. It's very, very slow to extract data this way, unless you're using quad SPI. But normal SPI for 64 megabytes took me about a day. So it's almost like 9600 baud all over again for internet. So if you don't want to be intuitive, like I prefer to pull chips out. And the thing that I like to use is this thing right here. So what we can do with this right here is it will hold 2 of the 8-pin chips that were on that image. And it will go straight to a breadboard. And you just push this straight in, put the chip in, and it locks right in. So I don't have to worry about soldering things, make my own breakout board, and put in solder paste and heat gunning it and make sure everything's right. I can just rip the chip out, put it inside of there, and then breadboard the rest. So if we don't be intuitive about it, this is a great way as well. This is known as a SOIC, in this case 8 for 8 pins clip. It's about $6 or $8. So again, if you break it, it's not a big deal. But this way you can clip onto the chip and also have a nice leads, off the chip itself. The only thing, you're gonna have to supply power to the chip. And I've never come across this yet, but there are stories about people breaking the actual components around the chip as well when they've supplied power. I've never come across it, but just be careful of that. So my personal method is to rip the chip off, but this way works as well. So exploitation. This is what we care about, right? Like all the other stuff, we can Google this all day and we can figure it out ourselves. So exploitation. So a lot of code that I've seen in embedded devices is almost like if you've been in on an assessment, you'll see test code being used in production, like debug messages, right? So in this case, this particular binary is catching all the seg faults and reporting back the return address and where the program counter was. So I'm like, cool. So just using this, not using GDB at all, I can cause the crash, get where my return address is. I can also analyze the function exit to know what other registers I have in my control upon crash. So this is pretty basic, but yeah, it's debug code inside production. Cool. Let's use this. So crafting the exploit. So like I said, it came from the x86 land, right? Desktop space. And I created the same 2 functions and disassembled them side by side. But the thing is though, I care about exploitation right now. I want to get them shells, right? So the very left one, we can see the leave instruction, and then we can see the return. So we know off the bat we have EBP in our control with a direct value from the stack, and we also know that was ESP plus 4 or 8, excuse me if I'm wrong on the offsets there, will be in our control via deref. We look at the return address for the MIPS one, we see a stack address being popped, loaded from the stack offset right there into RA. So RA is the return address, is dedicated register in MIPS, sitting just using using ESP and hitting return. So we have a dedicated return address, and then from here we see the offset 30 into FP, which is S8. And then we do a jump to RA. So if we look at this in GDB land, we can see what we can predict, right? We look at the function exit upon crash. EBP is in our control, ESP is in our control as well, and do the return EIP, right? So we compare this to MIPS. S8, which is the FP, is in our control as well, and RA is in our control as well. So this is great. So we know exactly what's going on. So if we can just cause the crash, and we know the RA is in our value, we just look at the function exit, we know exactly what registers in our control. So we can craft our exploit pretty quickly with that acknowledgement. And we can also learn how jumps and everything and returns work as well in MIPS based on the jump and returning aspect. So next we have to go instruction hunting in libc, right? We have to craft our exploit. In this case, the base address for the MIPS vulnerable binary, and a lot of them do this as well, have a null byte in the greatest significant bit. So partial overwrite may work for the first try, but if you're trying to wrap your way around, it's not going to work within the binary itself. So in x86, you know, if you do a basic stack buffer overflow, everybody knows the easiest way is what? Jump ESP, win, right? It's pretty basic. Pretty basic. I'm talking about no NX, nothing like that. Pretty basic. MIPS, on the other hand, is kind of a pain. So I look for maybe jump register, stack pointer. No, try again. Maybe move the stack pointer to T9, and then maybe I can call T9. No, try again. So MIPS exploitation is a little bit different because we have a reduced instruction set that's within libc that we can abuse to our advantage, right? So crafting the exploit, I had to use 4 gadgets in order to get SP into a register at an offset that I liked to call it. Like that's kind of a pain, but yeah, this is what it looks like. So the way I was able to do this was by looking at everything I've done before in x86, translating that over into MIPS, and it works beautifully. So all I had to do here is find my offsets, replace the libc address with the one that's on the binary on the device itself. ASLR is not working on this, so it just doesn't work. So we know our libc address is never going to jump around. So within Radar, because that's what I use for disassembly, I don't care what you use. You can use IDA, you can use whatever you want. But the one thing that's super frustrating about all this are the null bytes. So anyone who's ever done shell coding or anything else knows this frustration. But in MIPS, it feels like every single instruction that you have within your control that the processor can understand has a null byte somewhere. So it's pretty much a pain. So unless the thing you can do is create an encoder, like an XOR encoder, but you know, that's basically what we can do. So if I need some instructions as well, I use RASM for my assembler. And all I did here is a simple trick that I use to null out a return address that was getting in the way of my exploitation. So I just XORed a register, put it in that register. So S0 is null. All 4 nulls is no operation. It's kind of like hex 90 and x86. And then afterwards, I store that at an offset that I know where that return address is so it doesn't break my exploit. So I use RASM for that. So in a nutshell, with these type of devices, I've seen newer devices, like I have a newer MIPS device where the ASLR does work, but the entropy seems very low. It only looks like about 1 or 2 bytes are changing, but they're pretty predictable. But that's a different story. For these type of devices, like the one I have right here, it's not going to, the libc address is not going to change. So grab the libc address. You can also do this in QEMU as well. You can emulate all of this. And that's what I did as well. So all I had to do was emulate it, and then from there just change the libc address, and it worked beautifully. Find your offsets, craft your shellcode, which is magic, and then you can test your exploit in QEMU. I use userland statically built QEMU, and it works great. Sorry. So I use statically built QEMU, but the problem is with your shellcode, you're going to get a connection back, but it's going to segfault. It's just going to error out. I've been trying to investigate as to why it does that within a CH-rooted environment, but that's what it does. So testing shellcode on here may not be the best approach for emulation. A full-blown QEMU system may be the best bet for this, but for quick, easy, dirty stuff, if it connects back, whatever, let's test it on this and see if it works. So like I said, replace the libc base address with your target, and then boom, we get profit. So this is one of my examples. So I have a project I'll talk about towards the end. It's called DVRF, the damn vulnerable, this and that, but this is the router firmware. So this is a basic stack buffer overflow where I'm actually doing a partial overwrite of the return address to jump to a function that's within that binary that has no calls anywhere else. So I'll be writing about these as well. I took the same exact exploit. I changed the padding a little bit just for my own self. and it worked exactly the same. I don't have to change anything. So whatever works in the emulation, 99% of the chance it's going to work on the actual device itself. But going forward, one thing I want to advocate, and I'm guilty of this, and I'm pushing forward to not do this anymore. This needs to go away. I am sick, and I was doing it myself, and I am sad that I was doing this, but having proof of concept saying I caused a crash, EIP, or the program counter is all 41s, I win, drop mic. This is only half of the battle. I believe anyone can type in all A's and get a crash and call themselves like an elite hacksaw or what. So going forward, no more DOS pox. Let's make pox great again. So going forward, all the exploits that I'm writing, they'll be going to exploit DB. We'll do code exec, and no more of this. Hey, I got pointer control. No, none of this. Also, I ordered those hats. They're coming in about 2 weeks. So if you would like one, sync up with me. So this is the part that I enjoy. So I'm going to do a demo. But the mentality of this is to keep this a little bit fun, right? You guys don't like when I just stand up here and talk very monotone and stuff like that. So I want to make this a little bit fun, keep you guys' attention. And so I have an actual exploit, but the way I'm going to deliver the exploit is kind of through like the Hollywood way. Like we've seen those Hollywood ones with the guys with the masks on, like ski masks or the balaclavas on, hacking away with this, high energy music. But we look at it and we go, that's not hacking. He's not actually hacking, right? That's bull. That is not how that works. Well, I'm going to make that work today. So I'm going to take that whole scenery that we just talked about, the whole mentality, and I'm going to craft an exploit and exploit this device Hollywood style. But first, I got to set up the environment. So first things first, within this device, I need to introduce the FTDI USB chip that I have right there so I can get UART connection, because the binary that I'm going to be exploiting is only accessible through the UART because I don't have any scripts in there upon boot up to execute it. So part of this project is to force you to do the hardware aspect of this as well. So with this, I'm just going to be lazy and look at my screen history. And I didn't type history right. That's great. Yeah. So 173, right? Cool. So now we have UART access. And within the pointable, I have something called shellcode required. And then we have this socket BOF, and it's going to take a port. So now this vulnerable application is now listening on the port that I defined. So we're halfway there, right? So the next thing I'm going to do is I'm going to have a netcat listener for a reverse shell. So before I do anything, I just want to triple check everything because it would be embarrassing if this didn't work the first time around. So 113, yep, all right. So now let's do this. All right, hold on. I gotta set up even more, so hold on. I gotta set this even more. So, all right, so like I said, all right, so I'm going to start hacking right now.
Hello InfoSec Southwest. This demo exploits a stack buffer overflow vulnerability in this MIPS device. But first, we need some sick hacking music. That's better. Now we need to cover our tracks for that offset. Thank you.
So I'm really glad that worked. So yeah, so we have complete code execution on here now. We're inside the device. If I control C my netcat instance, we'll see the other one just return back. So we have proof that I did exploit this. So that was the exploit that I was showing a little bit earlier with the 4 gadgets and everything else. It took about 20, I would say about 15 hours because I was teaching myself that assembly stuff on the fly. So let's go back to the presentation. So that was my little demo. Thank you all for sitting through that. So the differences that I learned from this. So x86, basic stack buffer overflow is Very, very simple. Yes, yes. That's what we all agree on. Jump ESP, easy to kind of craft shellcode without null bytes. We're doing subtractive and negative numbers, all that good stuff, right? We know all this stuff. Wrapping, just get control of ESP. Yeah, it's exactly what we know. So if we have the right value executed, we know +4 of that's going to be our next return pointer. Super simple. MIPS, on the other hand. So basic stack buffer overflows, have fun trying to find a jump stack. Yeah, have fun trying to find that. There's something called instruction cache, and on some websites, like especially Craig's, there's something called cache flushing. Looking at linuxmips.org, they have stated that only some of the MIPS processors, more of the newer ones, utilize this type of architecture, well, implementation. So there is no need for any, like if you have an R3000, you don't need to flush the cache to get exploitation. Wrapping is required just to get stack pointer execution. It's kind of crazy. Wrapping itself, I'm looking into this now. I'm just trying to find a MIPS processor that I can buy that has NX capability. As of now, everything has been executable, so I'm still on the hunt. So if you have any devices like that, please sync up with me because I really want to test. Want to test the stuff going forward and rehash all this. So in a nutshell, the thing was the same. So exploiting code without a GDB server. So I have GDB host and server that I've cross-compiled for the MIPS, one little Indian and big Indian architecture, right? These will be on GitHub. We're going to try to push this out today so everyone can have them. There's been other GDB servers I've seen compiled, and they throw illegal instructions. So this one will work on every single MIPS processor to my knowledge because I've tested on many different ones. I have a MIPS 2 and MIPS 1, and it works beautifully. So without GDB server, we can use JTAG. So how many of you guys actually heard of JTAG? All right, cool. How many of you have actually used JTAG? All right, cool. All right, good amount. That's great. So if we have JTAG access, right? So we own the kings of the kingdom at that point, right? We are the processor. Like we control everything. We can control memory. We can control register values, set breaks. We can halt the processor. We can control everything. We are God at this point. If we don't have JTAG access, it's basically the same steps that I did and I showed you guys. The whole emulation stuff, testing it out emulation-wise, teaching yourself the assembly, and then just like replacing libc address on the device and just crossing your fingers. So JTAG. So this is an Arduino Zero that I bought. The reason why I bought it is because it utilizes the Cortex M0, and a lot of embedded devices that don't use a full-fledged operating system, that don't have a memory management unit, will use a Cortex series for real-time operating systems, like FreeRTOS. For very low trivial tasks, like let me query this sensor and see what the update is. So this is the JTagulator, and what I have here that I've accidentally stepped on is a Arduino, I believe it's the Arduino Nano. It was about $15 off eBay. And this device will actually do the same thing as the JTagulator, but there are some differences. So this, you can use something called JTAG enum. It's on GitHub. It's free. It's the same logic that the JTagulator uses. You just won't have any voltage control. So on this, I believe you're stuck with 3.3 voltage logic versus JTagulator. You can adjust it in software to be 1.8 to 3.3, which is great. This doesn't have any input filtering or anything like that. So if you blow this up, it kind of sucks. JTagulator does have protections. So to each their own, if you want to do the cheap method, this is a great way to do it. JTAG enum is the project. So with the JTagulator, you bind to the serial interface, all that good stuff, and you have it just go crazy, right? You just connect the pins everywhere. Make sure you got ground first. You connect the pins everywhere, and you just have it go crazy, right? So when it comes back, it will tell you, like, this is the output, this is the input, this is the clock, and this is how many devices are connected to it. Great. We can also test it. So if I send something through the output should be the same as well, and they match. So now we know we have a JTAG interface. That's half the battle. So what I've used is something called OpenOCD, on-chip debugger for Linux. It works great. It's easy to compile. And once you have the configuration made for your destination processor, it works beautifully. And for this, so the way that it would work is that the FTDI is going to be your interface, and then you're going to select your chipset at the end, and then you're just going to merge the two configuration files together. So once it gets set up and everything else like that, you'll have a local GDB server instance for that processor itself. And it's default on 33333. You can change that within the configuration. You can change it. So 4444 is going to be the OpenOCD configuration menu. And from here is where you can start crafting the commands that you want to execute when it loads your configuration file. So from here, you can type in help, you can look at measuring the clock, you can initialize JTAG stuff, you can reboot the entire thing. It works great, but it's pretty straightforward. So if you have a JTAG interface, don't stop there. Just use OpenOCD. The configuration file for the FTDI chip is on Zifiter's website. For the Shikra, they're the same chipset, the FTDI232H, so you can use the same configuration file. And Adafruit does have pinouts for these things as well, so you're not guessing like, what is this? So it's it's not very simple. It's straightforward, but it just takes a little bit of time when you're first getting into it. It may not be as straightforward. But once you get it, it's awesome. And with the Cortex series, you can download the datasheet for it as well and look at the memory maps for all the different areas that it's allocated to. Like I can look at maybe application data. I can look at different memory regions. In one assessment, I was able to pull AES keys for some sort of protocol that I'm not going to go into. But yeah, so if you have JTAG, you win, and you can craft your exploit very quickly, and OpenOCD is the way. So closing up, the one thing I want to talk about is my project. The project that I demonstrated right here, it's called DVRF. And just like we have everywhere else in the world, we have the damn vulnerable web application, Node.js, Linux, everything in the world, right? So I decided, well, there's nothing really out there that has the hands-on experience for users who are interested in getting to embedded device hacking, right? Like we have blog posts, we have all this stuff, but no one really has like a binary to extract, to use binwalk, to upload to an actual device and install it. So that's where this came from. And I had this E1550 laying around in my closet, collecting dust. So I was like, all right, little guy, I'm going to either break you or make you into something kind of useful. And luckily, I kind of rolled a, yeah, it didn't break. So that's all that matters. So this one is a MIPS 32-bit little Indian running a MIPS 1 instruction set. So that's what the binary is built for. And you can do this both ways. You can either buy this device, which is like, I think like $5 or $10 on Amazon or eBay now. It's a very inexpensive device. Or you can emulate it. I encourage to do both ways. Emulate everything that you have, all the binaries first, and then if you want to get the actual device and put the binary on there, you'll see that they're pretty much the same. So I encourage both ways of doing this. And also any kind of like developers who are out there thinking, I want to make a small form factor device, like I want to make a smart, I don't even know what's around here, a smart hat. Like you can do that, but just be careful of how you're programming this, especially if you're a first-time C developer. This is where the GitHub page you can download the DVR project from. You can download it, fork it, erase it, I don't care. A new version is coming out where I'm writing a blog post about the exploitation stuff I did for this, the hardware stuff that where you can buy everything, get started. And I got an idea from one of the researchers here known as Rich Johnson to create a Docker or Vagrant file. So you have a VM with all your tools already on there. So you don't have to worry about, all right, I got to install a Linux VM and pull all the tools. I'm taking care of that. I'm trying to make this as easy and seamless for you guys. This is my way of trying to give back to the community of stuff that I'm learning. Because if I can learn it, you guys can learn it in like 2 seconds. That's how I'm seeing it. So future plans, I'm continuing development DVRF. I'm going to be expanding now into the ARM territory. So after this, I'm probably going to go to Fry's, pick myself up a AC68U, which I know is an ARM, I believe V7. So I'm going to be using that, going straight forward, using the same techniques that I used to teach myself MIPS, and doing that for ARM. And I know it's going to probably be a big pain. If there's any kind of ARM assembly guys in here, please warn me. So that's about it. So the exploitation stuff, I'll be writing about that. I'm taking apart everything. There's my Twitter if you guys want to hit me up. These are the references. They're very small, so you can't see them, but they will be online if you guys. I'll be posting these guys slides for ISSW. The software that I use, the blogs. This is the end of my presentation. So are there any questions? Yes, Brandon Perry.
Hi, do you use the pattern create and pattern offset scripts in Metasploit when you're doing the original?
So when I had the verbose error messages when the crash happened, it's exactly what I did. Pattern create and then pattern offset, and then that's how I was able to go from 43 Cs to 44 Ds within the crash that I showed in the examples. But that's the very first thing I did, but I wanted to know what other registers I had in my control. So when I did the GDB cross-compiling, which is statically built, I saw the registers were in my control, and I just looked at the function endings, like when they returned. I'm like, oh, well, that makes sense now. So yeah, so this is exactly what the first thing I did, pattern offset, pattern create, and then from there, I did use GDB, but I use it in QEMU userland equipment using -d and then having a port open for GDB server and craft the whole exploit and just replace the libc address. Any more questions or, comments, concerns? Want me to do the demo again? I'm not going to do the demo again. Yeah. Meet me after the talk, and we'll get you signed up with a hat. There's colors red and black that say "Make Pox Great Again," and on the back it just says "No more DOS Pox." So no more capital A's, no more of this. Hey guys, I got a super elite, exploit. It crashes. No. So any more questions or comments? Yes. Huh? So yeah, the things that I'm posting are going to be on Praetorian's site, the company that I work for. My personal blog is kind of turned into dust, kind of now as of lately. There's really not much activity going on my personal site. So everything I'm doing or any kind of new things will be posted on Praetorian's blog. Any more questions? I'll take that as a no. Thank you.